Hello everyone, and welcome to the first MDPI webinars on coatings, entitled Advanced Coatings for Buildings. Thank you very much for joining us today. This is the first webinar of this series based on the sections from our Coatings Journal. If you are interested in submitting your paper to our open special issue, you can find more information on the webinar webpage. Today's webinar will have three chairs. First of all, Professor Anibal Maury-Ramirez, who is the current Dean of the Engineering Faculty of Universidad del Bosque from Bogotá. His main scientific contributions lie on the development of sustainable building materials, particularly on green walls and roofs, photocatalytic materials, nanomaterials, and sustainable concrete. The second chair is Professor Inês Flores-Colen, an associate professor at Instituto Superior Técnico from the University of Lisbon, and a researcher member at Research Unit Theories. Her expertise background covers the field of construction, civil engineering, and coatings. And finally, Professor Hideyuki Kanematsu, a professor of material science and engineering at the National Institute of Technology at Suzuka College in Japan. His areas of interest include biofilm engineering, surface engineering, corrosion, and STEM education. We will also have Dr. Giovanni Borsoi as a speaker today, who is a researcher at CERIS, Instituto Superior Técnico, University of Lisbon, who will give a talk about building exterior claddings. After all the talks, we will have a final discussion and a Q&A session. So if you have any question, please feel free to post them in the Q&A box. I would also like to remind everyone that this webinar is being recorded and that we will also have a YouTube live streaming today. The recording will be posted on the webinar webpage for everyone to watch it as soon as possible. So that's all for my part. I will hand out now the microphone to Professor Maury-Ramirez. So everyone, enjoy.
Good morning, everybody. Here in Colombia, good afternoon there in Europe, and good evening to everybody who is in Japan. Thanks a lot for just being here. But also I would like first to thank to all the personnel from MDPI and Coatings for making this webinar possible, and also to make possible all, the publication of our book on advanced coatings for buildings. Specifically, I would like to thank to Ana Sanchez, who is presenting today, and Raynor Shaw, that is also working in the editorial of coatings. So first of all, I will start showing you the program for today. First, we will have this introduction that is given by myself. Then we will follow up by Inês Flores-Colen, who will introduce and present important challenges of protective treatments. Then we follow with Dr. Giovanni Borsoi, the effect of hydrothermal aging on hydrophobic treatments applied to building exterior claddings. Then Professor Hideyuki Kanematsu, we present antifouling coatings, followed by another presentation of ultra-low biofilm materials and coatings. Then we will have a last part for questions and answers that will come from the audience. So many thanks to all of you for being here, and I hope you enjoyed this webinar. So first of all, the question probably you came to your minds based on this title of the electronic book is, first, what is so important, or why is so important to have a publication on advanced building materials? Well, first, buildings are used in all societies to give housing, services like education, work, and so many others. And it doesn't matter in which city or which country you are, so you will find buildings globally. For example, in this screen, in this picture, you can see that buildings are used in Hong Kong, San Francisco, Abu Dhabi, and New York. All of these cities are known for being so big, but also located in different environmental conditions, and they have different backgrounds, different histories, and however, they share one thing, and this thing is that the buildings are done with concrete or reinforced concrete. Concrete is the most used material not only for those cities, also for developing countries, So Colombia, Bogota, here is the window of my apartment, and you can see how the intensive use of concrete has been developed. So concrete data shows that the production is the biggest by far from other building materials, even than steel and even wood and polymers, of course. And this is basically because concrete is cheaper than the other materials. And it's also some other reasons I consider important to mention this, because it's available everywhere. So you can find the components, water, cement, rocks, mostly in any place in the world. Also because you can work with people that have not a high training or that doesn't require high training. So it's easy to work with many people compared to other techniques like steel, for example, the second largest used material for buildings. Uh, Normally, you will require for those building technicians that can do welding and use proper tools. So still have some disadvantages compared to concrete. Then we have a very critical point, that is durability. Concrete is more durable compared to the other ones. It doesn't mean that it's eternal, but still some properties associated to durability are better than the other competitors. For example, for wood and steel, you will have to do a lot of maintenance activities very often. Then we have another property. We have that is moldable. What does it mean? That concrete can have different shapes, and it doesn't matter where is it located. So based on only on the casting place, you can obtain the shape you want. Compared to steel and wood, is not the same, because steel cannot be casted in situ for a building, or is not commonly done, because it will demand a lot of high temperature for doing this. So basically, these are the reasons why concrete is so popular worldwide for doing buildings. However, as I mentioned, durability is one of the main issues, and surface of buildings are so important to avoid durability problems. But basically, to understand what the topics we are going to talk today, it's very important to understand what are the mechanisms of damage of building structures, specifically on concrete structures. So you can have four main reasons associated to damages to building. For example, we have mechanical, consider one big group, physical, chemical, and biological damages. All of them are really critical and important for the long lasting or the life cycle of a building. So improving this relationship between a good design, a good material based on mixed design, for example, of concrete, or an excellent construction process will guarantee somehow that the building can resist all these demands from the damage mechanisms. For example, mechanical damages are associated to loads. What does it mean, loads? Well, for example, a building that was designed for housing cannot be changed to library or introduced or changed to a factory, because the loads that was considered for the design are only for living families and not for equipment, and vibrations can cause a very big damage to building. That's, for example, one case, but also it's also very important not to transfer design from one place to another. For example, in a earthquake risk zone, you have to design very strong buildings compared to another ones, and you cannot just move them very easily from part to part. Physical damage is also very important part of the durability problems in buildings. For example, Fire, fire can cause a lot of damages in the physical and chemical properties of cement, Portland cement, for example, and that can reduce mechanical properties. So this is one point that has been studied so far for fire resistance of buildings. But there are so many other common problems, like increase of temperature by day and reduced by night, and those produces volume changes in the elements or in buildings, and that produce damages. There are also another group of big damages in buildings that are very common too, and are the chemical and biological damages. Normally they come together, but it's not always the case. For example, when a structure is in contact with water, some of the minerals of the water or the liquids, they can affect durability of materials. So underground water normally have a lot of potassium and sodium components that can affect the durability of the footings or the cementation of a building. That's also considered important in water treatment plants and so many other structures. And it's also very important because it's very combined with the biological deterioration. What happened with this? Well, some microorganisms, because they found nutrients, fixations, media, and light and wetness, so they can fix on the surface of the building material and cause deterioration. Later on, I will briefly introduce this very important concept to all of you. Also, as an engineer or as an architect, you have to design buildings, materials, and construct it so properly that you can avoid all of these situations. However, the situation is not like that. So you can find in any cities all these damage mechanisms, and there are a lot of maintenance activities associated to that. So in order to avoid this, for new buildings and existing buildings, there is a possibility to design and use advanced coatings, which are really important for the future of sustainability. So you not just can design coatings for increased durability, but also to give new properties like air purifying and self-cleaning properties to buildings. So this is very important for what we are going to talk today. But I want to remind you what are those mentioned phenomena that are going to be talked today. So corrosion is one of those. Probably steel corrosion is one of the phases you will remember for what is durability problems associated to reinforced concrete. However, the problem, it doesn't start from the corroded momentum. The momentum or the problem starts with the carbonation. Carbonation is the first phase of corrosion, if you can call the problem associated. So carbonation starts with the diffusion of carbon dioxide into the surface of a building material and the production of calcium carbonate that reduce pH of the concrete, making it susceptible of corrosion, specifically in places where the humidity is very high, salinity and temperature are high. So corrosion is very easy in those places. That's why marine structures are always or normally corroded, but design of advanced coatings are required in those cases. The same for this case. Marine structures in general, or places where the humidity is very high and light is not so intense, microorganisms find it very interesting to make colonization of the surfaces. It doesn't matter if it was just the problem of a color thing, but they can degrade the material. So in the first picture, you can see there is an algae colonization of a marine structure. Also in the upper part, you can see a building colonized by a fungi that has increased his size significantly in a huge manner. Also, there are some structures containing water that can have this situation, and some places inside indoor housings that are very critical, for example, not only for the building, because also they can affect human health. And we are talking about serious stuff in developing countries, for example. But how is the mechanism working on? So microorganisms find a place where to fix. All the surfaces are not the ones they want. They look for surfaces that have a very low pH, high roughness, porosity, and a not too intense light, but accessible, very random to light, and also some humidity. So these are the conditions that microorganisms that are like algae, bacteria, fungi, and some others find it interesting to grow on. And then they feed of these nutrients, grow and reproduce, and during this biological process, they release some acids and sometimes introduce some roots in the building material that they seem very simple in a human eye scale, but they are really important what durability is focused on. So they can decrease really durability, affecting the integrity of the element or the building. So these elements normally die and they develop they are part then of nutrients that become useful for new microorganisms and more sophisticated and more complex to avoid. So in the first stage, coatings can avoid the growth of microorganisms, and that's very important for increasing building durability. So these are the microorganisms that has been very often studied for avoiding with advanced coating technologies like bacteria, fungi, algae, lichens, and molds. However, there are so many interesting things happening today. For example, SARS-CoV-2, that is the virus that caused COVID-19, has been studied with photocatalysis to be degraded because photocatalysis releases some substances that are able to stress the virus. Viruses has no cell wall, but still can affect their biological process. So very interesting for about what is going on in the planets. There are some other damages in buildings that are very important because they demand a lot of investment in maintenance. However, they are not critical in the failure case. Some architects consider that aesthetical appearance is also a possibility of a failure. So in New York, for example, you can see in this picture how the soot, that is a substance that is generated during the combustion of fossil fuels, is fixed in the surface of this building fachadas. So the maintenance is very expensive and very often increasing the cost of operation of a building. So coatings for this are also available in this book. This book then goes to the application of advanced coatings for durability, so increasing the life cycle of a building, to another thing, to increase novel functions to buildings like air purifying and self-cleaning and antimicrobial and antivirus properties. These are really new trends to make sustainability in buildings and of course in cities. This book is available in this link that you can find below the picture of the cover and a brief abstract of the book. The topics are very diverse, as you can see. So we will talk today of advanced protective coatings for buildings, one, nano coatings with air purifying properties, anti-fouling coatings, ultra low biofilm materials and coatings, biological coatings for buildings. This is a very interesting topic because it also considers biological coatings as an ally of a good thing in the building system, improving thermal, hydraulic, and another environmental issues associated to sustainable construction. So biological coatings are also a way to improve the relationship between materials, traditional in civil engineering and construction materials, in the environment. So, and probably this approach has been one of the oldest one. For example, in the Babel Tower, biological coatings were used for reducing the interchange of heat between the exterior and indoor of the tower. And they are still related in several books. There is also an evidence of using biological coatings like green roofs in medieval time. So in the Nordic countries, they also use these covers to reduce the interchange of cold with the interior and the outdoor of the buildings. This also has been included by the modern architecture. Le Corbusier included one of the main aspects in construction and improve and include green roof as a technology to reduce the impact of urbanization in cities. So this book also deals with this topic. So how to use biological coatings in a good way towards buildings performance. And in this case, Naranjo et al. Developed a research based on the study of different recycled and reused materials to integrate or to compose green roofs that were evaluated at outdoor conditions in controlled rainwater systems. For example, The drainage layer of a building of a green roof in a building is normally composed of natural aggregates. In this case, this was replaced by recycled rubber coming from tires, very problematic topic in the world, PET bottles, and a PET bath. So all these systems were compared towards three things: weight, that increase mechanical damage; second, hydraulic performance, that absorb water and release it to the pipelines to evacuate rainwater. Normally is very efficient system. And then we have another topic. We have the thermal isolation. I think this is a very interesting approach for this new generation of green roof systems. So the idea of this is to improve the relationship of urbanized areas in cities and integrate them to the ecosystem where they belong to not only developing functions to the building, but also improving and giving things to the environment, like air quality, growing of biological species, and so on. Agricultural, urban agriculture, so many topics come with this. And there is another interesting and advanced topic, what is called photocatalysis, that is being studied and developed worldwide by Akira Fujishima from Japan. In the 70s, Professor Fujishima intended or tried to simulate what plants do with photosynthesis. So using carbon dioxide and solar energy and some water and minerals from the plant to absorb CO2 and produce O2, oxygen. So he, using nanotechnology, tried to degrade some pollutants in air and some other things that are affecting the durability of a building. How is it works? It's a little bit more complex, but I will try to explain it very easily. So a titanium dioxide nanoparticle is a semiconductor particle or material which has a valence band and a conduction band. When this material is in contact with UVA light, so an electron from the valence band will accelerate or will energetically be activated and move towards the conduction band. Then this electron will have a hole behind charged positively. The difference between those two will have or will represent the band gap. The electron and the hole will interact with oxygen and with water present in the atmosphere and will produce super complex and degrading substances like a super radical oxide and hydroxyl radical OH. Both of them have a strong degrading capacities, not only for decreasing air pollutants, inorganic and organic. They will have also the potential to reduce substances in a solid state. For example, decreasing the cell wall from algae and breaking them down will help the system to reduce the growth in the building surfaces. This is very interesting approach that has been studied also in this book. So the application of these technologies are already applied or used, in some cases in pilot projects worldwide. In Rome, for example, you can see the titanium dioxide photocatalysis applied for self-cleaning properties in this church that was constructed by Mayer for the anniversary of 2000 of Jesus Christ. Also in Belgium, in the coast, in the north part, in Ostend, a building has 5% titanium dioxide as a coating in these building fachadas. So the results are not completely fine. So that's why so many research is published in these books, because efficiency is looked for by changing the crystal structure of titanium dioxide, by adding external atoms, for example, and so many other strategies like incorporating recycled glass and so many other stuff that you will find interesting for your read. So many other applications, as I mentioned, are used for air purifying properties. So paving stones, including titanium dioxide, have been used in Hong Kong for reducing air pollution. So next to one of the main sources in the urbanized areas that are normally cars, so paving stones are included as a medium to reduce air pollution. Also in Belgium, in Brussels specifically, in this case, so we found a tunnel, Leopold II, that includes titanium dioxide covering that using UV light improve and increase the photocatalytic activity. That's also included in the paving stones in Antwerp in Belgium. So all these strategies are looking forward to an advanced system of construction that not only resists the low demands of the use of a traffic or some other stuff. The point is to give new functions to materials based on the demands of the environment. I guess this is one of the main points of the future in advanced coatings. Finally, this research also has been included by Italcementi and is evaluating the inclusion of a big area of Milan and evaluating how will be the impact in air quality for these major cities. Results are very promising, specifically based on dry conditions, so summer conditions, but not so promising for winter times, where the water puts in contact with the nanoparticles. Basically, are these the main or major topics that you will find in this interesting book on advanced coatings for buildings. But I will leave you the word to my colleagues, to Professor Inês Flores-Colen, who will talk about the importance and challenges of protective treatments. Really important for also durability and giving new functions. Many thanks to all of you. See you soon.
Hello, everyone from Portugal. It is a great pleasure to be here. First of all, I would like to thank to MDPI and Coatings Journal for this opportunity, and also to my two colleagues, Professor Anibal Maury-Ramirez and Professor Hideyuki Kanematsu, to share the edition of this ebook. I hope this is the first step for new future collaboration. Today I will briefly talk about the importance and the challenge of protective treatments, and maybe for discussion later. Concerning the protective layers, the purpose of these protective layers can be minimize defects during in-service condition, for example, through maintenance actions, can be improve other properties of the coatings, hydrothermal performance, fire reaction, increase the durability of coatings, especially maintain or improve the performance during the life cycle of the facade and the building, and also allow multifunctional coatings. Within the WGB Chilled Research Project is a national project that we have been working in this coating. This is a multi-layer coating. Yeah, you can see on the top right. This is a coating that has a layer that is a thermal insulating layer. It can be mineral wood, EPS, or cork, and that has also a base coat mortar with a mesh and a finishing coating. Usually the manufacturers use acrylic, silicate, or lime-based finishing. So this coating system has been increasing a lot its application, especially on facades, to improve the energy efficiency of buildings. This is the case in Portugal and also the case of Europe. This project has a multidisciplinary team, as you can see their faces, from technical and from also the National Lab for Civil Engineering, LENEC. They have different backgrounds, scientific backgrounds, nanotechnology, biotechnology, chemistry, georesources. So we have different knowledge, and it is very important for this kind of project. And this project is also funded by our Portuguese agency is FCT. According to this coating, we have a European guideline. Here you can see 004. This guideline indicates a service life for this coating system, a service life above 25 years, and also indicates some criteria that mainly is based on mechanical and physical functions, but, for example, does not consider the surface condition in urban environment. For example, the resistance of graffiti cleaning, the resistance to biological colonization or pollutants. And as you know, the combination of these degradation agents with water cause anomalies. So the criteria to minimize superficial anomalies, these anomalies, and control also the efficiency of protective solutions are missing for this coating system. If we understand the synergies of all these degradation agents and also the protective measures, so we need to understand that to resist to water, it's better also to resist to biological colonization. So the synergies that we can combine with indicators or criteria, if we do that, we can set up a new criteria that complement the existing criteria for this guideline. So it's important to do that for protective coatings. And here we are talking about anti-graffiti product, hydrophobic agents, biocides, self-cleaning, and other multifunctional products. So here I summarize the challenge for protective treatments, and I think it will be good if at the end you have, if you agree or not, or if you have other suggestions. But in our opinion and our research, we identified these. So what are the challenge of protective treatments? We need sustainable solutions. So I think there is no any doubt during the life cycle of the building. So it's not only in the beginning, it's during and at the end of the cycle. So we need solutions with low environmental impact, for example, low carbon emissions, for example. We also need a reduced and low ecotoxicity, especially in the leaching products during the in real conditions. And also, we must also bear in mind the circular economy, which consists of reusing materials, recycle materials, as Professor Anibal talked about it, and also incorporate waste. So it's important to go forward to sustainable solutions. Also, we need to develop durable solutions, or at least predict regular maintenance. If we take the benefit from these synergies, we can develop better multifunctional protective solutions. Also, we need to fulfill new demands, especially legal, but it can be also user demands. I have here two examples: energy efficiency, human health and comfort, but there are other demands. And also to better tackle the climate change, now a big word nowadays. So we need to have also adaptive solutions. So in this case, I think is also another challenge that we engineers and professionals, chemists and other professionals have to in terms of the climate change. So all these solutions also have to be, should be economically feasible during the life cycle, especially not in the acquisition phase, but also during the life cycle and at the end of life cycle. So the tools that we have here, the LCA, the life cycle assessment for to test environmental impact, and also the LCC, the life cycle costing tools, should be applied when we develop protective treatment. So to overcome all these challenges, we need innovation and multidisciplinary knowledge. So this is an idea, but maybe you can have other ideas or other suggestions that we can put in this list. So I hope that you enjoy, and thank you. I will stop the share and give the word to Giovanni.
Hi there. So good morning, everyone. So I'm gonna share my PowerPoint presentation. Give me a minute. Yeah. I'm gonna give a brief presentation on hydrophobic treatments on exterior claddings. So basically the purpose of the research that we are carrying on in Portugal at the moment is based on multifunctional products. So as Professor Inês Flores-Colen already introduced, we're not only focusing on hydrophobic treatments, but still we know that hydrophobic treatments are the base. Since most water can be considered particles indeed, because it's like the beginning and the end of most of, not life, but also most of building materials. Since it's the prerequisite of life, it's also a major cause of decay, since it usually triggers physical, chemical, and mechanical degradation and decays. Basically, what we are looking for is to reduce the penetration of water, and especially the retention of water, and so to balance somehow the moisture transport properties within the building material, especially when we are dealing with porous building materials. And in this sense, hydrophobic treatments can be effective because they can effectively reduce the modify the contact angle, basically. So we are looking for something that is somehow with an higher surface tension. So the application of this non-polar material can repel water, which is a polar substance. And of course, well, this is simple to explain somehow, but then there are a few prerequisites which should be respective when dealing with hydrophobic materials, especially when dealing with built heritage like limestone or mortar. We need three requisites, which are compatibility, durability, and effectiveness. And compatibility, it's a big issue most of the time, because we know that we need to respect the physical and chemical, and of course, finally aesthetical feature of the substrate. And on the other side, we need also a strong durability or long-term durability of those agents, which should somehow increase the life cycle if we're dealing with modern materials, or even like century-old materials like mortars or historical mortar or limestone, for example. Another requisite is the in-depth penetration if we're dealing with, of course, porous materials. So we need to consider that most of those treatments are not reversible. So we need to do the right choice. We need to be aware of which are the possible drawbacks and by side effects. And yeah, and this is the base. Though then, if we look at the most used hydrophobic treatments in the market at the moment are silicon organic compounds. So basically those materials, some like silane, siloxane, and or other resins, are based on silica and functional with the alkylic group, And those usually have a lot of benefits if used as a hydrophobic product, because usually you have somehow an high resistance to oxidation processes, especially in the brand new paints or in the brand new products, and an extreme pH environment resistant. But on the other side, we know that there might be problem related exactly to those two components, especially after a few years. On the other side, there is a wide application of those materials also because there is an aesthetical compatibility and they're kind of easy to apply. And yeah, they form an hybrid or mineral substrate on the treated material. Then there is an issue, which is still the durability, because we know that most of the manufacturers are not reporting the durability. They're just arguing like 3, 5, 7 years till 10 years, and which is something that is kind of ambiguous, because it's difficult to do the right choice sometimes for a specific material, especially they're not providing much information about the compatibility among materials and the specific products. So we're entering, this is the main question, because we know that there is somehow a compatibility among silica organic compounds as a hydrophobic materials. On the other side, we know that there is a problem of durability. After a few years, there are problems arising. And so we don't know exactly which are the dynamics beneath those issues. So the durability and effectiveness is somehow are going on the same level. And we need to, yeah, maybe we have like a super hydrophobic materials in the first 2-3 years, then there is a degradation, and we end up after a few years with a problem. So we are basically accelerating the decay of the material, because those irreversible treatment cannot be taken out of the treated materials. So in this research, basically we have focused on few materials, so the cement-based couple of materials actually, so a limestone and a mortar. And we have been focusing also on silane or siloxane products, a siloxane product. And finally, the third product is basically an emulsion of silicon and titanium oxide nanoparticles. Basically, those are the methods. So we have been applying the materials with a specific process, which you can find on the special issue. Actually, all the details are on the special issue. I will just give an overview about that. And then we have been focusing on the moisture transport properties, so the capillarity, water absorption, the drying, the Carsten's tubes test, and the water vapor permeability. And finally, we repeat all those tests after artificial aging. So I'm going straight to the results. What we can see here is that, yes, there is a strong influence on the capillary water absorption, and we're dealing with those silane or siloxane based materials, especially when in the case, for example, if we look at the stone, there is a strong reduction up to 88% of the water capillary absorption. And on the other side, you can see that, yeah, there is a linearity among all those products. And after artificial aging, we still have a quite high reduction of those values. And yeah, we can see that, for example, can be quite unexpected that maybe we're expecting that the capillarity is decreasing after artificial aging. But for example, with the stone, with the limestone, probably there is a poor feeling due to the artificial aging, which is influencing and increasing the water capillary absorption. On the other side, we can see that those two silane or siloxane products are quite linear. On the other side, we can see that there is an inverse trend after aging. So we can see that after artificial aging, there is a reduction of the water capillary absorption in the case of the nanostructure product. Somehow we can see that, yeah, the mortar is not much affected, because in both cases there is a high reduction of this water capillary coefficient, and somehow this is reflected also on the Carsten tubes test. And the same trend can be seen also on the limestone. When we look on the other side to the dry synthetics, we can see that in the case of the limestone, we can see that in all the cases the liquid phase evaporation, so the first step of drying, end up after 1 day. So in all the cases there is a 24 hours, there is basically there is an inversion of the drying process to the vapor phase. On the other side we can see, and this is the limestone, on the right you can see also the mortar, and in this case you can see the variation, so the transition from the liquid to the vapor phase is usually up to 4 days. So those two materials are very different because of the porous networks. And once again, if we look at the dry index, we can see that actually there is a slight decrease of the drying index after the application of the hydrophobic products. In the case of the nanostructure product, this decrease is very low, and it ends up similar as well after the artificial aging. So that, yeah, it seems that this material is pretty suitable. Those nanostructural products are pretty suitable for this kind of limestone. Then there is also another interesting part, which is the water vapor permeability. We can see actually that, yes, there is a huge increase. So the hydrophobic materials are really affecting the water vapor permeability, and mostly the siloxane-silane products is affecting strongly this behavior. On the other side, like the nanostructure is kind of more compatible, or at least less invasive compared to the others. And after artificial aging, once again, the nanostructural materials is much better because there is lower reduction of water vapor permeability. Once again, the limestone has a very different behavior when compared to the mortar, where the porosity is much higher, the pores are bigger, and so the reduction is lower because the product cannot completely fill the porous network. And so basically we can somehow resume what we have seen in the previous slides. So basically we can see that there is, if we look at generally at the application of the hydrophobic product, we can see that, yes, there is a reduction of the capillary absorption, and that is what we are looking for actually. So those are positive somehow properties. Then the second one, which is the drying index, we can see there is a differential behavior among the limestone and the mortar. And we can see that this balance should be respected. That is, the drying time should not be modified, because, I mean, if you're looking for a very compatible material, you need something that is not affecting completely the drying phase, the drying index. On the other end, at the end, we have also the water vapor permeability, and we can see that, yes, for example, in the case of this siloxane-silane product, there is a huge decrease of the water vapor permeability, increase, sorry. And so for sure, this is something that we are not looking for. We're looking for something that is slightly affecting this value. And so once again, respect the properties of the original material. So to conclude, since I'm already almost out of time, basically the main lesson I would say, yes, and that you need to fine-tune the effectiveness of the water repellent based on the properties of the treated materials, and of course based on the topology of hydrophobic product that is applied on those materials. Then for sure, for example, the limestone has a much lower absorption compared to the mortar. So you need to consider this. You need to look for something that is somehow respecting those physical properties. And then you need to consider that durability, which should be is somehow connected to artificial aging, to those artificial aging tests, are affecting in a different way as well the materials. For example, we can see that we have seen that the nanostructure material has a very efficient feature over time, but on the other side, these nanostructural silica and titanium-based materials are less durable, because those, after artificial aging, probably there is the decrease, and this is due mainly to the structure of the titanium side, which is linked within the porous network of the silica nanoparticles. Then we can see as well that we should somehow respect the dry index, and so all the materials are somehow strongly affecting this feature. And for sure, for example, in the case of the silane, for example, which has a much longer silica particle, and in any case, the molecular structure of this material is bigger when compared to silane. So usually those materials should be used for cement-based mortar, because you are looking for something that is somehow penetrating in depth and match the structure of this material. On the other side, the nanostructure material is more effective on the limestone, because they have a significant reduction of the water capillary absorption, but a very low reduction of the drying index and of the water vapor permeability. So it somehow is providing water repellency, but is respecting the feature of the original material. And finally, we cannot recommend actually the use of this siloxane silane product, because it's strongly affecting all the features of the moisture transport properties. So it's not recommended at all on both the treated materials. And to give also an idea about what is going on at the moment in the project, as already Professor Inês mentioned, we're also focusing on other features of the multifunctional treatments, because at the end of the day, we know that an hydrophobic product usually is also provides some anti-graffiti, for example, features. It also contains a biocide, so it has also an anti-fouling effect, or against fungi or algae and all those kind of biological colonizers somehow. And then on the other side also, when we're dealing with urban areas, we have also graffiti and pollutants, which are very invasive and can be a strong problem for substrates. And so we are, of course, evaluating all those features, and on the others, at the same time, you're also providing data on the durability, on the long-term durability, and both with natural aging and artificial aging tests. So I would like just to acknowledge the companies that provide the products and that are working with us somehow in the project, and of course the Technical and Scientific Foundation of the Ministry of Education of Portugal for the financement. And I will give space for questions eventually here or at the end of the session. So thanks. I will give now the speech to Professor Hideyuki.
Okay, hi, thank you. Thank you. So I'll start my presentation. Thank you very much. Thank you for a great lecture. Good evening to you from Japan in the Wednesday evening, closing to midnight. A moment, please. I will share my presentation file. Once again, good evening to you from Japan. I'm Hideyuki Kanematsu, speaking from Japan. This time, I will give the two continuous presentations. One is entitled the anti-fouling coating. You can see that. And the second one is entitled ultra-low biofouling material and coatings. And the two topics are very similar and related to each other. Therefore, I have been wondering how I could give the presentation and how I could differentiate the two presentations. And finally, I reached the conclusion, and I decided to give you that the presentation in the first presentation. That the first presentation will be about the general concept about fouling and anti-fouling, and what is how anti-fouling fouling is related to a biofilm, and why do we need anti-fouling coating. So the first presentation will be about the general aspect and the general concept mainly. And in the second presentation, I will move my topic from the general concept, philosophical one, to the practical materials topic. And in the second part, I will give the informative tips for you to develop the new anti-fouling coatings. And finally, I will give the concrete examples investigated by us, proposed by us. So even though my English is not good and my presentations may not be well prepared, hopefully my two presentations will please you and will give you some tips for you to develop the effective anti-fouling coatings in the near future. Okay, let's get started. This is the first presentation, anti-fouling coating. It is entitled anti-fouling coating. And this slide shows the main point, anti-fouling and biofilm. The technical words anti-fouling or fouling are often used in marine environments, ship, marine structures, etc. But in this presentation, I focus on biofouling. The word is related closely to the concept of biofilms, my research topic. Biofouling is the process of microbial attachment to materials and the following phenomena, all following phenomena. So biofouling is a process, and the biofilm is the matter. Sorry. And since biofilms forms on materials, the correlation between biofilms and materials is very important. Therefore, coating will be needed. This slide shows what the biofilm is. For all of you, this is a very common. This concept may be well known. However, at the beginning stage of my presentation, I need the slide. A biofilm is any group of microorganisms in which cells stick to each other, and often these cells adhere to a surface. This biofilm is actually a water film. It contains lots of water. Water is dominated in the biofilm. However, another components another components exist. Two components are very important. One of them is bacteria. One of them is bacteria itself. And another one is extracellular polymeric substances derived from bacterial activity. It is called EPS, extracellular polymeric substances, EPS, we call that. So biofilm contains lots of water and EPS and bacteria. Therefore, since the EPS is contained in the biofilm, the water film is very sticky So you can understand very well that biofilm is closely related to corrosion, because this is a water film, and unfortunately for us, this is very sticky film. So it is kept on the material surface eternally sometimes. Biofilm affects many industrial problems, industrial fields. This slide shows that. Sorry, the characters are too small for you. Maybe too small for you. Biomaterials and the infections, reefs and the seaweed beds, materials degradation in soils, cooling water, hygiene problems in the food industry, and ship or marine structures problem, and corrosion or ballast water, and many others. And recently, very important problems appeared. As you know, since at the end of last year, COVID-19 problem occurred. In such a case, we are afraid that human matter and human infection may occur. I mean, infection occurs through matters. For example, human touch the door or wall, then virus or bacteria move from the human to the materials. But on the material surface, they don't lose their activity, and another person come to the material and touch the material. Then the second person may be infected. Such a problem occur, and antibacterial problems, antibacterial market, including a virus and the bacteria and the biofilm, is increasing very rapidly nowadays. Therefore, anti-fouling coating is nowadays very important. The important is increasing nowadays. So this slide shows how the biofilm formed. Maybe you know that very well. So I will give you the brief explanation very rapidly. Bacteria is floated in the environment. However, they are hungry. They always need a nutrition. But nutrition is an organic compound, and the organic compound very often absorbed on the material surface, because material surface is unstable from the viewpoint of energy. Then the attachment increases, continue, or some bacteria may detach. However, such attachment and detachment process may repeat, but finally the attachment process exceed the detachment process. Then the number of the bacteria increase on the material surface. Then the number of the bacteria reach the threshold value. Then bacteria excrete polysaccharide simultaneously, and material surface, including a bacteria, are surrounded by a sticky water biofilm. That is the biofilm formation. So how can we develop the anti-fouling coating? Before that, we have to produce biofilms artificially in the laboratory. We need the method, common method, if possible. And then we have to have the evaluation method. But the two general methods have been missing. Therefore, my colleagues and I have to establish the biofilm production process and the evaluation process in a couple of years so far. This slide shows that biofilm forms, first of all, in the laboratory, and then we have to observe. that quantitatively or qualitatively. I will show some examples of the production ways investigated by us, by our research group. This slide shows one of them. This closing system is composed of pump, column, and reservoir for the bacteria. Bacteria exist here in the culture media. For example, LB culture can be used, and inside that, for example, Escherichia coli may exist, and the bacterial solution pump up and flow in the closed system by this pump, tubing pump in this case. And in this column, specimens are placed, and the flow of the culture media form biofilms on the specimen. According to the in the previous slide, in such a mechanism, biofilm form on the specimen. That is one of the methods. In this method, a single piece form biofilms. For example, Escherichia coli. But the general interest is how the environmental biota, mixed germs form on the material surface, and how the environmental, does the environmental biota form on the materials. This apparatus, we devised this apparatus to investigate the effect of environmental biota and the effect on the materials. The system shown in the previous slide, as the system shown in the previous slide, this also this closed system is composed of three components: column, and tank, and pump. And specimens are placed here, materials are placed here. And then the pump circulates the water, tap water, just the water. Any liquids are available, but usually we use the water, just the water, tap water. And the tap water circulate in this way, and at this place, the system is open, and water is flown down on the plate, and fan is blown on the plate. And at this point, the environmental biota, the many kinds of bacteria in the air are mixed here, and this process is repeated, and then 7 days or 1 month or 2 days or 3 days, biofilm form on the specimens. And we could observe and analyze the difference between the antibacterial specimens' antibacterial properties. And then, biofilm forms in the laboratory biofilm reactor, which I have shown you just right now. And then we have to evaluate how many biofilm form on the materials, and we have to compare the biofilm quantitative number of biofilms among the specimens. Therefore, we have to develop the methods. This is one of the methods. Sorry. This is another method. I have shown you the flow type laboratory biofilm reactor, but in this case, another static method. Plastic wells. I show you right now. Plastic wells and specimens and the bacteria culture specimens are put into the well, and each well is filled with the bacterial solution. Then they are put in the incubator for a couple of days or a couple of hours. Then after the incubation, we remove the specimen and then we analyze the biofilm on the material surface. How could we evaluate the biofilm quantitatively or qualitatively? This slide shows that there are many methods, but we always focus on the two methods. You know, EPS is the characteristics of biofilms. Therefore, one of them is a Raman spectroscopy. Raman spectroscopy enables us to analyze the organic matters on the material surface. Therefore, we use the Raman spectroscopy. However, this is not suitable for quantitative analysis. Companies always need the number, a concrete figure, concrete number, you know, 3 or 4 or 5. Therefore, in such a purpose, Raman spectroscopy is not appropriate. It is appropriate for academic research. However, this is not good for quantitative analysis. Therefore, usually we use crystal violet and its staining. This slide shows that crystal violet absorbs the polarized part of the molecules, and then and the color is changes in violet color shown in this slide. So usually we use such a method, you know, biofilm forms, and then we stain the biofilm by using 0.1% crystal violet, and then the stained crystal violet is dissolved into the surface active agent, for example, sodium dodecile sulfate or ethanol. Sodium dodecile sulfate is recommended, but anyway, it is dissolved, and light of 570 nanometer, irradiated. Then crystal violet absorb the light of 570 nanometer specifically. Therefore, we can evaluate the biofilm quantitatively by measuring absorbance. And in such a way, we analyze the antibacterial, anti-fouling properties of materials. And at the same time, if we develop the anti-fouling coating, then we can evaluate the anti-fouling properties quantitatively and correctly by using this method. As I show you at the beginning of the presentation stage, biofilm affects many industrial fields. Then, coating. If the coating will solve the fouling problems, it will be applied to not only to buildings. Building is very important purpose, but in other fields, there are many problems caused by biofilms. Therefore, such a coating will work well for many industrial parts. And let me continue with the second part of the presentation. Yeah, the second part, second presentation is entitled "Ultra Low Biofouling Materials and Coatings." Yeah, now you understand what kind of measurement we will carry out usually. Then next step, we have to develop the anti-fouling coating. I'll explain about that in the second part. This slide shows the contents of the second part. How can we find, develop, and evaluate anti-fouling materials? I have already told about that. But what kind of materials could control fouling and biofilms? how can we differentiate the materials among the many candidates? And a concrete example by our research group, from the viewpoint of a copywriter, I will show you our group's development and devised coding. I will show you them. This slide is already explained. This slide shows the mechanism of biofilm. But in this slide, also in this slide, let me stress, the biofouling properties, biofouling process is composed of multi-steps. Therefore, a coating may work well at one point, but another concept may work well. Therefore, the very complicated problem this is. This slide shows that. And coating materials are classified into 3 parts according to the material science. Metallic materials, ceramics, and polymers, they have their own energy to make the condensed matters. Therefore, we have to classify into 3 parts. The metallic materials, in the case of metallic materials, ionic metal dissolve into metallic iron, and they exist into the environment. And this iron have the strong interaction or weak interaction with the bacteria or the proteins around the bacteria or biofilm themselves. Therefore, some metal works well, and another metal doesn't work. For example, iron metal attracts bacteria very strongly. Therefore, from the viewpoint of a surface coating, we have to stop the dissolution of a metallic iron into the environment. That is the guideline for antifouling coating. Copper, people say sometimes copper have antibacterial properties. However, copper basically have the strong interaction with the bacteria. Therefore, at the beginning of the stage, copper iron may work, but with the time being, copper gradually lose their antifouling effect. Or such a discussion would be possible. Ceramics is classified into 2 types: bioinert ceramics, like silicon nitride or silicon oxide, or not silicon oxide, sorry, aluminum oxide, or silicon carbide, or something like that. They don't show any van der Waals force in the outside of the specimen. On the other side, in the group bioactive ceramics, the material has a strong correlation between interaction with the bacteria or biofilms. So some ceramics work well for antibacterial properties, but another ceramic doesn't at all. And polymers are classified into 2 types: polar polymers or non-polar polymers. From the viewpoint, I believe that we can arrange some polymers. This is this slide shows one of the polymers. On the polymers, how do components interact with bacteria or bacterial environment? Van der Waals force or electrostatic force may work simultaneously or independently. It depends. And hydrophobicity and hydrophilicity are also important problems. But as for the concepts, there are many contradictory results. Some people say that hydrophobic polymer would accelerate to form biofilms, but another person deny that. Therefore, maybe the reason could be attributed to that biofilm formation is composed of multi-steps, as I showed you in the previous slides. Therefore, at some step, hydrophilicity and hydrophobicity work differently. And another step, another factor may be involved. Therefore, it is very difficult to determine the effect of hydrophilicity and hydrophobicity on the biofilm formation. Personally, I observed that hydrophobic polymer will be good to protect the biofilms, but it depends on the combination of materials, environment, and bacteria themselves. So various stages of biofilm formation and interaction forces, as I told you, the biofilm formation is composed of multi-steps. What kind of steps do we aim to develop antifouling coating? That is a very important problem. And this is one of the coating methods investigated by me and the colleagues. I had a patent for that, but I gave it up because any companies are not interested in them. In this case, the substrate material was ceramics. 2 layers formed one by one. For example, in this case, I succeeded in the 2 layers of silver and tin. Tin doesn't have any antibacterial properties, antifouling properties. However, silver has a strong resistance about the fouling phenomena, against fouling phenomena. Then the 2 layers were melted each other by adding the heat. Then the intermetallic compounds form. And the intermetallic compounds of, for example, silver and tin showed us the very high antifouling properties, because silver dissolves into the environment gradually. Gradual dissolving is very important. And polymer brush is also another one. Polymer brush, maybe my time is running, so I will show you the very brief explanation. This is a polymer brush. Polymer brush is also one of the promising coating method against fouling phenomena. And this one is I got the patent, Japanese patent, and I still hold that because it is going to be sold. Well, silane compound is the substrate, but silver, nano-silver, or nano-copper, or nano-metallic antifouling metals are dispersed into the coating. So it shows very high antifouling properties. As shown in this slide, this composite coating is very good to, I think, privately. Okay, that's all. Thank you. My time is maybe over. I'm sorry for that, but that's all for my presentations. Thank you very much for your kind attention. Thank you.
Thank you, Professor Hideyuki, for your talk, and everyone for your talks. So we will do brief discussions. We have plenty of questions in the QA box. If you want, we can start with you, Professor Kanematsu.
Yeah.
I have a couple of questions for you.
Yes.
We have a couple of questions from Farsin Gadani.
Oh, thank you.
He's asking about if you have any standard testing method to evaluate or verify the degree of sterilization for the water that you use in your circular system.
Sorry, I can't follow your speech. You are talking about the staining method, right?
A sterilization method. In order to know that you are free of bacteria for the water that you are using in your circular system.
Your environmental biotas flowing laboratory reactor. Okay, yeah, I see. If you don't mind, let me show the screen, okay?
Okay.
As you can see, specimen is placed in this point, at this point, okay? And water is flowing in this direction. Therefore, shear stress occur on the specimen surface. That is an important factor to form biofilms. And bacteria, try to resist against the flow. Then they attach to the material surface. Then the number of the bacteria increases and the biofilm forms. That is my answer.
Okay.
And the flow, if with the flowing rate, the bacteria forms well.
Okay.
They form very strongly to the material surface if the water flow exists. That's my answer. Hopefully, my answer will be you.
Also, Professor Inês wanted to ask you if the synthesis of biofilms, if the biofilms are industrialized and commercialized for buildings, and if yes, which substrates are used to apply the biofilms?
Oh yeah. Recently, I have technical, a company came to me and asked my collaboration for the purpose. The building for one of them is just a wall develop fungi, but the fungi, why does fungi forms on the wall? Because at the initial stage, biofilm must form. Then at the beginning stage, the bacteria started the biofilms. However, biofilm forms, then nutrition and the water exist. Therefore, at the next step, fungi come, and fungi will developed. Therefore, but to control the fungi or something like that, or biofilms, we have to develop the antifouling coating on the walls. That is one of them. And another one is very important. People in the building industry doesn't know about that so well. But in Japan, people are going to realize the phenomena. That is the pipeworks in the building. In the building, in a mansion, many pipeworks are developed. Okay, tap water's pipeworks, or discharge water pipeworks, or there are many pipework networks exist in the building. But inside the pipeworks, inside the pipe, biofilm forms and develops to form scales, and to solve or to avoid the scale or to remove the scales is very difficult. Nowadays, many companies maybe use epoxy coating, but it is not enough. I believe so. Therefore, a new coating method should be should be developed. And as I told you, I mentioned the silane compound composite coating. That is my recommendation.
Okay. We have also a couple of questions for Professor Anibal. So the first one is from Raynor Su. I just wondering the economic performance of green roofs like recycle or reuse materials. And what about the cost derived from installing, maintaining, upgrading, and disposing these constructive components?
Many thanks, Anna, and many thanks, Raynor, for the question. Actually, it's one of the major concerns how to evaluate the environmental, social, and economical impact of a green solution, of a green roof, using recycled, reused materials. For example, we are trying to implement a whole city with vegetated surfaces of green roof and green walls in order to improve thermal, hydraulic, and so many environmental issues in a city called Cali in Colombia that is 3 million citizens. So in order to evaluate that and give practical tools to the decision makers, you have to give a life cycle assessment of every green solution. For example, the idea of doing this life cycle assessment for green roofs is to change the construction from an economical system based in a linear way so that you have extraction, processing, use, and disposal. For economical perspective that is more circular and includes recycle and reuse materials. So then we have more like a extraction of environmental goods that is not the same that extracting just rocks from the environment. So you have to compare that extraction phase from one place where you use natural and non-renewable resources compared to this waste incorporated into green roofs. Then we have the processing that already doing this processing is you have less energy consumed. And also you have in the use phase, sometimes even better performances than when you use natural aggregates for the drainage layers. So perhaps you have in this case, for example, in this research contained in this book, you will find that you have better thermal performance for rubber recycle than the rocks. And it's because of the physical and chemical characteristics of rubber in this case. So it's an isolating layer and it works very well. Then you have other parts of the whole life cycle assessment. And we have even in the waste, the possibility to reuse it for several life cycles. So I consider that we have to do a more systematic way of doing this evaluation to give a proper answer. But already this publication gives you an idea of how is the performance for some specific aspects that are the major ones, for example, in the accreditation for sustainability. So that is already in the publication.
Well, Professor Inês wanted also to ask you a couple of things. First of all, it's about the durability of the photocatalytic protection on concrete, if you have any kind of value, and which are the most common fungi that you can find on concrete, if you know a specific species like Aspergillus or something.
Correct. So I have, for the first question, durability of photocatalytic coatings and in general photocatalytic materials is one of the major discussions globally because they are really efficient under controlled conditions. But once you put them outdoor conditions, you will have some degradation of them. We have been evaluating different mechanisms of degradation of those photocatalytic properties. For example, just by accumulation of dust. So this application in the streets will bring a lot of dust into the materials. And just by the accumulation on the surface, you will have a very complicated photocatalytic reaction. So based on these results, we have to improve the efficiency, and we are going to the nanoscale to improve the efficiency of the nanoparticles by doing a structural modification and being able to absorb more energy, not only the UVA wavelength, just widening the wavelength to a bigger band gap. So we want to improve the efficiency of the material, but also by improving the whole structure system. For example, by doing modified porosity, modified roughness, and also including glass recycled to improve the photon penetration in the material surfaces. That's one of the major things. And for the fungi, unfortunately, I have not done research specifically on fungi, only on algae, and it's it's another kind of algae, and that's it. But for the moment, I haven't done research on fungi. Thanks a lot.
Thank you. For Professor Inês, Parthin Gadami is asking if you can describe more specifically about the layers that you are talking in your presentation. He's asking for slide number 3. If you can talk a little bit more about the key layer, the coating.
Okay, maybe I can share.
Mm-hmm. Yes.
So this is we call ETICS, is an external thermal insulation composite system. If you want to know more, you can consult the guideline that I mentioned. This is a guideline 444 that is only specific for this system. So in the layers, you have a thermal insulation layer. We are studying 3 types of thermal insulating layers: mineral wood, EPS, and it's like a cork. We use a lot in Portugal. So we have this is a thermal insulating layer. We have a mechanical fixing to the substrate or not, but usually you have a mechanical fixing. And then you have a mortar. Usually this mortar has resin, or is not only cement, because you need to have some strength. But because of sustainability and durability, also the manufacturers are trying lime. But this mortar intends to guarantee the boards, because this thermal insulating layer is a board. So we have 2 thin layers, base coats with a mesh. And then we have the finishing. So in this project, we are studying the finishing, because if, for example, if you have cracks or if you have problems on the surface, you can, during the service life, you can affect the performance of the whole system. Because, for example, if you go and you have water in a mineral wood thermal insulating material, you have a bad performance, because it's not good to have water in this kind of thermal insulating. So it's too important to study the finishing coat for other types of degradation agents. So I think it's clear. And then you have different details, it's like metallic details, to guarantee all the protection of the corners, the below part. You have the email, and if you have any questions more about it, you can send to me.
Okay,
Thank you. Thank you for the question.
And I think this is for Dr. Giovanni. If not, correct me. How did you select the accelerated aging protocol? Is the hydrophobic effect due to the chemical nature or to of the particles, or to their size?
Yeah, I already saw the question. Well, when we are dealing with these artificial aging protocols, we are always adapting specific tests from other materials. In this case, as I mentioned as well in the PowerPoint presentation, this is the new European norm, is the 1050-21, which is based basically, we talk about the determination of the compatibility of mortar for external purposes, let's say, so external renders. So among those tests, there is also a specific test for artificial aging evaluation. And we adapt, and we have many years of experience and many tests done with this kind of tests, and actually it's working, and it's already published and referencing each other. And then, of course, I'm talking about mortars and limestones. So for stone, there is also other types of possible tests. For mortar, this is probably the most suitable one. But then if you're looking, for example, to external thermal insulation systems, for example, ethics, there is another type of test, which is the ETAG, which was already referred by Professor Inês. So the ETAG 004 is something that is slightly different. But in any case, all of them are using extreme thermal shocks, basically, to evaluate through like freeze-thaw or heat-cold cycles to evaluate the durability. Yeah, few argues that, yeah, maybe 1 month, so 30 days of testing, which is like 80 cycles, repeat cycle of night and day, can be some around 5 to 7 years compared to natural exposure, let's say. On the other side, we are doing as well, as already Professor Anibal mentioned, when we're dealing with laboratorial condition, it's not the same of real exposure to, let's say, external exposure. In many parts of the world, there are extreme somehow weather agents depending on the season. So in any case, you have something that is influencing the durability, and there are synergies. For example, another problem with the nano titanium oxide is that it's somehow is working for is a UV activated, so you need the sunlight to activate it. But then there are the necessity to have some humidity as well, and possibly some thermal shocks to enhance the self-healing, or better, to the self-cleaning effectiveness. So in any case, even the laboratory evaluation of specific compounds somehow are neglecting something that is expected in natural exposure. On the other side, you have a control condition that somehow can exclude some variables, and so you can focus on specific aspects. And this is the case of this test. We can exactly understand if there are thermal shocks, which is exactly the behavior over time of those treatments. Then concerning the chemical or the let's say weathering part, so yes, of course there is always a chemical explication, and more details, technically speaking, are in the papers or in the ebook. But in few words, if we compare like silane and siloxane, we know that silanes usually have 10 to 15 Armstrong of dimension, then the structure is 10 to 15. In the case of the siloxane, we have 20 to 25 to 75. So the silane is much smaller, technically speaking. And so it's expected that silane is penetrating more in depth within the porous network, like in the case of for example, of a limestone or a mortar. And then you might prefer like those kind of smaller particle, the silane, compared to a siloxane. But on the other side, if you need like just a surface coating, so something that is not absolutely porous, so you don't need to penetrate the surface, you might want like the siloxane, sorry, because the molecular structure is longer, and so is expected to have a higher durability as well to weathering. So it depends on the application of those materials. And then, yeah, concerning the emulsion, finally, the mixture of the silica and the titanium oxide. Well, there is an interesting feature connected to the photocatalysis. So you can have some self-cleaning on one side. On the other side, you have features, you might have issues of durability. because we know that the silane is a coupling agent. That means that it's enhancing the adhesion to a substrate. But of course, the titanium is not actually a coupling agent. So there is a problem. If you're not using 100% silica-based product, you're losing some physical property over time, and you might have some durability issues. So you need really to somehow fine-tune the product that you want to have, you want to apply to the property of the material that you want to treat. This is the question, and there is an equilibrium among those properties.
Okay, thank you. So as the last question for Professor Kanematsu, Professor Anibal wants to know if you have evaluated coatings against viruses such as SARS-CoV, COVID-19.
Yeah. That is a very serious problems right now, as you know. And maybe bacteria. As for bacteria, biofilm is a effective reservoir for them. That is the truth, and many investigations, many researchers confirmed that. That is the truth. As for the bacteria, that is a very urgent future topic. But for example, virus keep the activity depending on the materials. That is the true already. For example, on the stainless surface, the virus, many virus keep the activity in 7 days, but in on the polymeric substances, virus lose their activity only in 4 days or something like that. But biofilms, I believe biofilms will be a good reservoir for virus because it contains water. Therefore, I believe so. But it is a very important topic. I'm now subscribing many funding using that. Therefore, please expect me in the near future. Yeah, that's my answer.
Okay.
Sorry.
So there's no more questions. So I just wanted to thank all of you, all the chairs and the speakers for today, and everyone for attending this webinar. So if you don't want to say anything else, we can close the session now.
Many thanks to everybody. That's all.
Thank you very much.
Thank you,
Thank
Professor.
you.
And enjoy.
Thank you.
Thank you.
Flores.
See you again soon. Bye.
Good night.
Good night.
Good afternoon. Bye.